That's cool. And it's definitely soccer season. Okay. Yeah, my son plays soccer, but I think they got washed out like Monday, Tuesday, and Wednesday. So, who do you play for, Adam? Oh, that's who my son plays for. He just started this year. He's in the U13. I'll have to ask you about it later. That's cool. Yeah. Awesome. Okay. All right. So let's get started so I can get you on your way on a Friday. Thanks for coming. I know that Aiden is out somewhere. So hi, Aiden. You're out doing your Lego Legion stuff. So hopefully that's going well. All right. So this is the last section that we're going to do in chapter 8. It's called mathematical induction. And so mathematical induction is it's another way to do a mathematical proof. So there's different kinds of proofs that we have in math, right? You did a lot of them, I'm sure, in geometry. We haven't done a lot in PreCalc. Bummer, right? But this is a method to prove that something is true. And you can see that there's two parts to this kind of proof. So we have let me zoom in a little bit here. Well, you can see it here in your blue box. Okay. So the principle of mathematical induction has two parts. The first one is, well, first of all, we have some statement involving integers. So we have P sub n is a statement involving the integer n. So typically these are series or sums of series that we're talking about. So that's why it's in this section. Okay, so if you want to prove that this statement is true, then there's two things we have to do. The first thing that you have to do is say, is P sub 1 true? So when n equals 1, does my, what do I want to say? Let me take a step back. You're trying to prove, for example, I'm number 8 down here. I have 3 plus 11 plus 19 plus 27 plus all the way up. So you can see that this is a series of numbers that we're adding together, right? And so someone has figured out, oh, when I add all these numbers up, that's the same as doing n times 4n minus 1. So someone has figured this out for us, right? And we want to prove that this is true. So that adding up all these numbers to whatever selected, we could go out, 20, n to n equals 20. So we could go out 20 spots that we're adding up. We could go out 100 spots. However far out we go, however many numbers that we sum up, we can just simply find the sum of those numbers by plugging in. For example, if we want to find what happens when I add the first 100 numbers up, then I would put in here n equals 100, and I could figure out, what that number is without actually evaluating every single term and then adding them up. It's kind of like our summation thing, but it's a little bit different. Okay, so if I want to prove that this is true, okay, then I have to do two things. The first thing is that I have to prove that it's true for the first number. So when n equals 1, right, is my answer 3? So I got to prove that that's true. When n equals 1 is my first answer 3. And then, so that's the easy one, right? That's like plug in, does it work out? And this is the theory. We'll get to the actual application here in a minute. The second thing that you have to do is a little bit more tricky, but totally doable. All right. So this one is that the truth of P sub k implies the truth of P sub k plus 1 for every positive integer k. Then P sub n must be true for all positive integers n. So this one's a little bit more tricky, but basically the big idea is that if you can show that for any series of numbers that you're adding together, if you add one more in that series to one side of the equation, and then you add one more on the other side of the equation, and it's still true, no matter where it is, then you can say that these are true. Okay, so it's a little bit wordy, but then I think when you, I don't know, at least for me, when I see it, it's like, oh, okay, I got it. All right. So let's actually get into some, let's try some of these. Okay, so the whole idea behind this whole proof is that we have the fact that we have to prove p sub 1 is true. So the first term is true, and that's pretty easy to do. The other thing that we have to do is we have to find p sub k plus 1 for the given p sub k. So this is some formula they've come up with for summing all of our values in our sequence together. And we basically want to find out what the next value in the sequence is. All right, so this is actually kind of 1 through 6 is kind of a warm up for what we're going to be doing in the actual mathematical induction. So it's kind of like the precursor to what we'll be doing, if that makes sense. So for example, if I take number 2 here, okay, see if I still remember how to draw on a computer. All right, if I take number 2 here, this is basically saying that if for example, I wanted to find for this series of numbers, what p sub 3 is, right? So I wanted to find, if I add the first 3 terms up in my sequence, what does that be? What does that equal? So I have, you know, my first term plus my second term plus my third term. What does that add up to? Well, that adds up to p sub 3. Okay, so if I wanted to find out what that adds up to, I would actually put in to my formula where I have k. So n is when we're talking about the theoretical. Okay, k is when we're talking about an actual number. So I would put into my formula what happens when k equals 3. And then I could, figure that out. So it would be 4 over 5 times 6. So it would be 4 over 30. That's what would happen if I added my first 3 terms together. Well, I want to know, again, we're kind of talking theory here. I want to know, can I find out what the next term is going to be, but in a generic way? So practically, my next term would be p sub 4, right? And I could plug in k equals 4 and figure out what my value would be, because you guys know how to do that. But I want to find out more generically, can I find out what the next term is going to be? So practically, how you do that is you take your initial equation, right? Have it here. And we know that p sub k plus 1 is just when we plug in k plus 1 for k. So in this particular formula, it would be 4 over, and then instead of k, I'm going to put in k plus 1 plus 2. Okay, and then instead of k in the second part of my formula, I'm going to put in k plus 1 plus 3. I'm going to make this bigger. Okay, so this is my next number in my sequence of numbers, right? If I'm going through and I find a sub 1, a sub 2, a sub 3, this is my next a sub 4. This is my next number in there. But this is in a more generic way. So if I have my next number, this is what it's going to be. Now, obviously we can clean this up a little bit. So we could rewrite this as 4 over k plus 3 times k plus 4. So doing it is actually not that hard, I don't think, right? But we just want to figure out what the generic rule for that would be. Okay, makes sense so far? Ish. All right, I'm going to clear this off. And we'll actually do some of these mathematical inductions. Okay, so in exercises 7 through 20, when we're actually only going to do 7 through 13, so that's kind of a portion of that. Use mathematical induction to prove the formula for every positive integer n. Okay, so let's take number 8 here. Instead of me rewriting it, I'm going to copy it and stick it over here. So you can see here that they've come up, I kind of talked about this at the beginning, right? This is a sequence that someone has come up. We have 3 plus 11 plus 19 plus 27 plus, plus, plus. And the way that they're getting each term in their sequence is they're taking 8 times the number minus 5. So in order to get 3, it was 8 times 1 minus 5 is 3, right? The second term was n equals 2. 8 times 2 is 16, minus 5, 11, and so forth. So that's how we've gotten every term in our sequence. This is not a arithmetic sequence, right? Arithmetic sequence. This is also not a geometric sequence, just a sequence of numbers. So somebody has figured out that when you add up all of these numbers, that we can simplify this as the number of terms that you have, right? N times 4n minus 1. So again, if I went out, 100 terms over here, I don't have to write out all 100 terms like in a table. I can just plug in n into this value and find out what the sum of all my values are. Okay, this is what's been proposed though, and I actually need to prove that it's true. Okay, and the way that we're going to prove that it's true is this method of mathematical induction. All right, so the first step to mathematical induction is the easy step, I think. And actually, I just kind of verbally said it. The first one is prove that P sub 1 is true. So show that this is true. So what we're trying to show is, does this side truly represent this side of my equation? Okay, so we already know on my left-hand side that P sub 1 is 3. It's already been evaluated for us, or we could plug in n equals 1 and get 3, right? And then on my right side of the equation, I'm proposing that it's n times 4n minus 1. Okay, so if I put in my first value, n equals 1, does this work? So it's 1 times 4 times 1 minus 1. And it is true. So the first part of my proof to show that this is true works, right? So that's the easy part. We like that part. All right. Step 2. Okay, and step 2, we basically need to prove that if we have P sub k, so any sum of the number, and then we add the next term, then my equation still works. Okay, so practically how we're going to do that, okay, is we're going to say, all right, we have all these numbers here. All right, so let's kind of take an easy example here. Let's say that we did P sub 20 over here. So we added up the first 20 terms, and we show over here that that equals P sub 20. Okay, if we do p sub 20 over here plus our 21st term. So notice I'm just adding the next number, okay? If I do, I add up my first 20 terms, just like I had above, and then I just add in what practically is the 21st term. So this right here, we're talking about the sum of numbers, and then this we're talking about one individual number. Okay, then I need to be able to show that that equals over here p sub 21. So practically, what does this look like? So it's a little bit weird. So let's add a little bit more. Okay, so we're just going to go a little bit generic here, and we're going to start using k. All right, so if I can show that p sub k, so any number, plus the next number at k plus 1 equals p sub k plus 1, then I've shown my second step in mathematical induction. So what does that practically look like? Okay, so what that practically looks like is we need to put in values for each of these. Let me make my chart a little bigger here. Okay, so on my right-hand side, I'm actually going to start on my right-hand side where I have my sum of all my parts, okay? So I know that the generic formula is n times the quantity of 4n minus 1. So in place of n, I'm going to put in there k plus 1. So I have k plus 1 instead of n right here times 4 times k plus 1, again, and where my n is, minus 1. Okay, so then let me do some simplifying. I have k plus 1 times 4k plus 4 minus 1. So I just distributed my 4. Right, then I have k plus 1 times 4k plus 3. Almost there. So when I get here, I'm going to use FOIL to simplify, and I get 4k squared plus 7k when I add my inside-outside plus 3. Okay, so this represents my next term in my sequence, my k plus 1 term. All right, so now I want to say, okay, what happens when I just have my, what happens when I use my left side of the equation and I'm actually adding all my numbers together plus the next additional 1? Okay, so what that looks like is over here. I'm going to color code that. Not yellow, red. So if I want to look at what is p sub k, that's just the sum of all my numbers, but not that last number that I have. Okay, so p sub k is actually going to be this same formula, but instead of putting in k plus 1, I'm just going to put in k. All right, so p sub k actually evaluates as k times 4k minus 1. So you can see instead of n up here, I put k in. All right, so that's my if I add up my first, in this practical example, if I add up my first 20 terms, that's my first k terms, right? Over here is that when I add up my first 21 terms, my k plus 1 term. All right, so I have my first k number of terms, but I still need to add in the next one, okay? And I'm going to do that. I'm going to color code this part, my next k plus 1. And to figure out what that next term's going to be, whether it's from 20 to 21 or k to k plus 1, I'm actually going to use my generic formula here. So I have 8, and instead of n, I'm adding my k plus 1, my next term. And in the practical, right, we're adding our 21st term right here, right? If we were talking about 20 and 21, or our k plus 1, we're adding the next one. All right, so once I've kind of figured out what that looks like, then I need to do some simplification, right? So I get my p sub k term is 4k minus 4. And then my next term, my k plus 1 term, is 8k plus 8 minus 5. And I totally forgot a squared here. And what was I doing here? Oh, goodness. I don't know what I was. Was I distributing 4? I must have been distributing 4. All right, this is k. When I distribute that, yep. Okay, so now I'm going to simplify all this together, and I end up with 4k squared plus 7k plus 3. So if you notice, this left side and this right side of my equation match. All right, so that's kind of a heavy concept. It's a little bit odd, but did it kind of make sense? Really make sense? Tell me what you're thinking. Yeah, that's how I felt, Sarah. I was like, it kind of makes sense. Okay, so let me just take this example here and just kind of walk backwards just a little bit since we have it up on the screen. I use black, okay? So mathematical induction is a way, big picture, we're just proving that it's true. We're trying to prove that if you add up however many terms in this sequence, you can simplify that as n times the quantity of 4n minus 1. Okay, we're trying to prove that that's true, and we're trying to do that by mathematical induction. The first step of mathematical induction is easy, right? You just prove that the first term is true for what you sum up to. Second part is a little bit more tricky, okay? So basically you're saying that if I add up everything I have, the first k numbers that I have, okay, and I add on just the next one, is that still true on my other side of the equation if I just go ahead and start with the next number? Okay, so for example here, the practical example that I was trying to use is that if we add up the first 20 numbers in here, right, and then we add on the next number, is that still true if instead we add up the first 21 numbers? So a super, super practical one would be, oh, what if we just add up the first 3 numbers, okay, and then we add on the 4th number, k sub 4. Does that equal the sum of my first 4 numbers? Because they actually tell us what the numbers are, right? So if I add up my first 3 numbers, I have 3 plus 11 plus 19. So that is 33. Okay, 3 plus 11 plus 19. And then I add on 27. Does that equal the same as 4 times 4? Oh, there's a ton of 4. Times 4 minus 1. And I'm running out of room. So I'm plugging into this side of my equation. Does that equal n times 4n minus 1? And my n is 4. And if you actually do the math, 15, 60 equals 60. So that's how we prove it's true, to show that If you have any number of terms and you add on the next one, then it's still true for your summation. Okay, so maybe we'll do another one just to make sure everybody gets that one, because it is a little bit weird. Not weird, just different. Not something we do often, right? And this won't have so much foil in it. We'll do number 12. And make it bigger. Okay. So number 12 says we have 2 times 1 plus 3 plus 3 squared plus 3 cubed plus blah, 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 plus 3 to the n minus 1. Okay. So however many 3's that you add together. So basically this is, this is 3 to the 0 power, 3 to the 1 power, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, 3 to the 6th, all the way up. Okay. And then we're multiplying by 2. If you add all those terms together, you could pick the first 5, you could pick the first 100. If you add those together, then you can find the sum by doing 3 to the n power minus 1. Okay, so that's what they're proposing is true. You could play around with a calculator to see if it's true for the first so many terms. But we're going to use mathematical induction to prove that it's true. Okay. So the first step in mathematical induction is to find out if the first term is true. Okay. So is my P sub 1 true? So this should be pretty easy because they've actually evaluated it for you, right? Basically, 1 is the first term on the left-hand side. So is 2 times 1, does that equal 3 to the first power minus 1? Because we're looking for when n equals 1. Is that true? So to get my left-hand side of my equation here, I just took my first term, right? And I'm not even worried about the rest of these. And it's 2 times 1 is 2, right? To get my right-hand side of the equation, I want to know, all right, I have 3 to the n power minus 1. And I'm looking when n equals 1. So 3 to the first power is 3 minus 1, which is 2. P sub 1 is true. Oh, we like step 1 in mathematical induction, right? Usually, if it works out. Okay. So now step 2. Okay. We need to show that if we add all of these up together, we add all these up together, so to some number k, and then we add on the next term, a k plus 1. We add just the next one. Is that the same as just putting in the next number? So basically, this is what you're trying to prove in step 2. You're saying if I add, again, practical numbers. If I add the first 100 numbers together, okay, so P sub 100, and then I add number 101 on, does that equal P sub 101? Does that equal if I just go ahead and plug in the next number? Okay. All right, so practically what this looks like is that P sub k and P sub k plus 1 are going to be, we're going to use this. So right now, P sub k is equal to this. All right, so P sub k would be 3 to the k power minus 1. And P sub k plus 1 is 3 to the k plus 1 power minus 1. So that's just these P sub k and P sub k plus 1 are talking about if we add up all of the numbers in our series, what do they equal to? What does this formula say that they're equal to? Okay. But we're can't just say they're equal because this is k number of terms and this is k plus 1 terms, right? So we need to add on to our P sub k, we need to add the next term, okay? And to get the next term, right, we need to use this value in here. So we have 2 times 3, and then it's really hard to see, this is n minus 1. So instead of n, we're going to put k plus 1 minus 1, and this is all in the exponent up here. Okay, and don't forget your 2 that's hanging out front here. Okay, so then when I start simplifying, okay, thanks for coming, Adam. We have 3k minus 1 plus 2, and then we have k plus 1 minus 1. So 2 times 3k. And then over here we have 3k plus 1. 3 to the k plus 1 minus 1. That's what happens when we clean it up, okay? So what happens if you have 3k plus 2 times 3k? That actually ends up being 3 times 3k minus 1. Okay. And then there's 2 ways that you could do about this. 3 times 3k is the same as 3 to the first times 3 to the k power. And if you remember your powers of exponents, you can just add those together. So 3k plus 1 minus 1 equals plus k plus 1 minus 1. So we've proved that it's true. Okay. Sarah, does that make sense? You want to see another example? Maybe try it and see how it goes. Okay, cool. I think since it's taken a little while, I'm just going to go ahead and finish up the last a little bit on Monday when we're in person. So let's see. I'm just looking back at our schedule. I don't think I have your homework's not due until the following Monday anyway. So I think I'll just finish up these last few that we have to do on Monday in class before we start chapter 11. So thanks for coming today, Sarah, and for being flexible, and I'll see you on Monday. All right, thanks. Have a good one.